We have talked about the idea behind thermodynamics and we have also looked at a specific instance of a thermodynamic system, even though it is an ideal one, called the ideal gas, the ideal classical gas. Now we are ready to look at the laws of thermodynamics themselves and explore a few of their consequences. The first step in doing the thermodynamics of a system is to identify all the variables, the thermodynamic variables. So let us start by writing step 1, identify the thermodynamic, I will use the abbreviation TD for thermodynamics every now and then, variables, both extensive and intensive variables. So we identify the set of variables, macroscopic variables, in terms of which the description of the system is possible and complete. Then step 2, and this is a slightly more difficult step, is to identify those extensive variables which provide a complete description of the system. So we may have a large number of intensive and extensive variables. On the other hand, a smaller set among this set of variables are going to be the independent variables. They define in some sense the response of the system to various stimuli. So we need to identify the independent set of extensive variables, and there are several ways of doing this. This is not unique. One way of doing this is the following, and a very common one, and the one that is standard, so to speak, is the following. If you have a thermodynamic system comprising, say, several chemical components, several kinds of molecular species all mixed together, then one has a so called entropy of the system. We will come back to this and explain a lot more about this, together with the volume of the system, and then you have to specify how much of each of the substances there is. So in some sense you need to know what are the number of moles, numbers of moles of each of these chemical components, or the number of particles of each molecular species. Let us call them N1, N2 up to N sub r. Now under normal circumstances this provides a complete set, at least for the kind of systems we are going to look at. This is a full set of variables in terms of which you can express everything else, and we have to say a lot more about what this S is. I mentioned a couple of times that if you label in equilibrium statistical mechanics, if you enumerate all the possible microstates of the system, namely you tell me what each details of all the relevant details about what each elementary constituent of the system is doing at any instant of time. You have given me a microstate, I now list all the microstates and take its log, and that is essentially the entropy of the system. In loose terms it is the measure of the disorder in the system, but it has got a precise definition, and we will see by experience, actually we will see what it is in certain explicit cases. Okay. Now given this set of variables, the idea is that you form what is called an energy function out of this. So we have a basic quantity called the internal energy of the system, one should use a symbol like E for it, as I have done on occasion, but use the standard thermodynamic symbol, the internal energy U of the system, and this is a function of all these variables in general. This is called the energy representation, but it is possible to have another representation in which you, it is a so called entropy representation, where you write S as a function of U, V, N1, N2, Nr. So let me write that down just for or S as a function of U, V, N1, Nr. These are equivalent ways of doing thermodynamics, and whichever is convenient, that is the one we choose. So once we have done this and we have got all the variables here, etc., we have the concept of what is called a state function. So what one does is, in the space of these independent variables, For instance, in the case that I wrote down here, u as a function of s, v, n, etc., etc. If you plot all these variables, you get a space, a certain space. So here is, for instance, s, here is maybe v, and here is a typical n. So if you had just one component, that would be the so called state space of this system. Then this function u here is a state function in the sense that at any given point in this space, for specified values of s, v, and n, you have a certain energy of the system, internal energy of the system. So there are every state function such as u is a function of these variables, these state variables, and the idea is that these functions in general most of the time would be smooth functions for which there would be partial derivatives with respect to each of these independent variables and so on. So the value at each of these points in the state space of this function u is supposed to be unique here. So this much for the mathematical part of it, but what use this is going to be put to will come in a minute, and that is where the laws of thermodynamics come in. The first law, as you all know, as you have heard probably, is just the law of conservation of energy, but we need to write this down in more specific form in the case of thermodynamics, and the way it is written is as follows. It says, if you take a thermodynamic system and you supply a quantity of heat to it, delta Q, an incremental quantity of heat, and let me write this amount supplied as dQ, not the usual kind of differential, but something called an imperfect differential. So I put a little slash there, that is just notation, imperfect, and I will explain what this means in a minute. But for the moment it is an infinitesimal quantity of heat supplied to the system, and suppose the system does some work for you, and let us suppose the amount of work it does is dW, then dQ minus dW, that too is an imperfect differential in a certain technical sense, which again I will explain very, very shortly. This is work done by the system then the remarkable thing is that the difference between these two imperfect differentials is a perfect differential which turns out to be du here. That is the first law of thermodynamics. This is the so called perfect differential. And what is meant by that? What is meant by saying du is a perfect differential is the same as saying that u is a state function. In other words, if at this point you have a certain value u and at this point you have a value u plus du, which is this point is attained by moving n a little bit, v a little bit, and s a little bit, and all the independent variables a little bit, then the statement is this is a perfect differential if you can write this du as a linear combination of increments in v, n, s, and all the other independent variables. So as long as you can write du equal to something times dv plus something times ds plus something times dn in this picture, it is a perfect differential where these coefficients, these somethings, are nothing but the partial derivatives of u with respect to v, s, and n respectively, and they are themselves functions of s, v, and n. So a so called perfect differential is simply the statement that this is a nice function of these variables, and the value at this point depends on the value of s, v, and n at this point. An imperfect differential on the other hand, such as this, would be a function which is not a state function. In other words, this incremental value here depends on the path which you have taken in order to get to the new point. So if you had a certain q here and a q plus dq, d slash q here, this value of this d slash q would depend on how you went from u to du. It would actually depend on the specific path, unlike the case of a state function where it does not depend on what path you choose. The general formula for du is simply this linear combination here with these well defined partial derivatives. So when you do not have this path dependence, you have what is called an imperfect, when you have this so called path dependence, then you have an imperfect differential. The work done is an imperfect differential, the heat is an imperfect differential, the increment in the heat, but the difference of the two happens to be a perfect differential. Now this is the way we state it mathematically, and of course this looks abstract, but the point is all this law was arrived at purely empirically from experiment. So a lot of experimentation and empiricism went into writing the laws of thermodynamics, but by hindsight, now in the benefit of hindsight, we can now write what the actual mathematical quantities are, and they turn out to be the difference between two imperfect differentials is given by the increment of a state function called the internal energy of the system, and its increment is a perfect differential on that side. So that is the content of the first law. You could rewrite it in various other ways. You could write it as dq equal to dw plus du. So when you supply heat to a system, it does a certain amount of work and the rest of it goes in its increment of its internal energy. This could be positive or negative. So this work could actually exceed this, and then this would become negative and so on. So there is no restriction on this thing at all. It is just that the sign convention I have chosen is such that dw is the work done by the system. Therefore minus dw is the work done on the system, but I prefer to use this convention here because it is easier and more physically easy to understand, because it says you supply heat, the system does some work, and then the rest of it goes in changing its internal energy. So that is the content of the first law. Now the most common example of dw will immediately make the position clear. The most common example is the case in which dw arises from a gas, for instance, which undergoes expansion. Equal to P dV. P is the pressure of the gas, dV is the change, infinitesimal change in the volume of the gas when it does some work, for instance by expansion, and then dW is P dV. But what you must note here is that dV is the differential, is a perfect differential, it is the differential of one of these independent state variables. So it actually says that dV equal to dW times 1 over P, and in terms of mathematics what it means is that when you have an imperfect differential like this, you can multiply it by what is called an integrating factor, to make it a perfect differential. So the statement in general is that when you have an imperfect differential, it might be possible to multiply it by an integrating factor, which is itself some function of some thermodynamic variables, which will make it a perfect differential in this case. So the way the first law is written in general for this case of this gas, for instance, is dq equal to du plus P dV. Actually it is a little more general than that. The most general form of writing the first law is as follows. You identify a set of intensive variables which are called field variables, and a set of extensive variables or response variables which are called state variables. So you have these so called field or intensive. Field variables happen to be intensive variables. I give examples right away, and then you have these state or extensive variables, and example, most common example, P here and then V, minus P for instance, so that our sign convention is kept straight. In general, stress, strain out here, you could apply an electric field to a dielectric. So, that is a field variable E, and then the dielectric would respond by getting polarized. So, the dielectric polarization P that is a state variable as a response. Then you could perhaps apply a magnetic field H. The system would respond by acquiring a magnetization M, and so on. So, you have a set of field variables and a set of extensive variables called the state variables, which represents a response of the system to the application of these field variables. So, in general one could call these some generalized forces F. Let us call it a generalized forces, and these variables let us denote these by x sub I, and these are generalized, they are called generalized fluxes. So, you have forces and fluxes or stimuli and responses in general. Then the first law in its generality actually says dq equal to du plus dw, which is equal to du minus summation over I Fi dxi. And the first of these f's is minus p, so this thing becomes equal to du plus p dv plus various other terms of this kind. For instance, if you had an electric field, it would be E, and then this would be dotted, it would be dotted with dp or h dot dm and so on. So, you would have a whole lot of these terms which would tell you what is the kind of work being done by the system under various kinds of stimuli or applications of fields. That is the generalized first law. A very important one which is normally neglected in elementary treatments, but which is important, very important, is the following. Even in the absence of external fields like magnetic fields, electric fields and so on, you could consider, you should really consider a thermodynamic system in which the number of particles itself can vary. Now, thermodynamic systems are of three kinds. First, you have an isolated system which has no exchange of either heat or energy with the surroundings, no exchange of matter with the surroundings. Then you have a closed system which can exchange heat or energy with the surroundings, such as a beaker of water kept in this atmosphere, a closed beaker. No water can get out, no air can get in, that is a closed system, but energy can be exchanged, it can be heated up, it can be cooled and so on. And then you have an open system where the number of particles itself can change, but matter can be exchanged with the surroundings and vice versa in addition to energy. So, in the case of open systems, you must also allow for variation in the number of particles itself. That is why I used n as one of the variables when I said S, V and n. So, when you use that, when you do that, then this law reads a little differently. This is equal to the first term here is minus mu dn, and you must use one of these for each chemical component, and therefore really the law is minus mu1 dn1 minus mu2 dn2 etc., where this mu, which is the conjugate variable to the n corresponding n, just as p is the conjugate variable, thermodynamic conjugate of the volume V, this mu is called the chemical potential. Corresponding to the chemical component 1. that I have labeled as 1, the molecular species 1 has a chemical potential. If you had another molecular species also in the mixture, then it would be mu2 and so on and so forth. So that is the sort of general form of the first law of thermodynamics, and we will write this in the following way for our purposes. Let me write it. Let us look at a single component system. So the first law of thermodynamics then is dq equal to du plus p dv minus mu dn. Okay. A single component with chemical potential mu, it is equal to this. This quantity mu has the following significance. As it stands, it is some kind of rate of change of this quantity with respect to n, that is the first point we see immediately, but it has got a better significance than that. It will turn out that this is the so called Gibbs free energy of this thermodynamic system per particle. So that is the physical interpretation of this mu, or to put it in simpler terms, it is the cost in energy for adding one more particle to a thermodynamic system under specific external conditions, under conditions in which the temperature and the pressure are kept constant. You add one more particle to a collection of objects, collection of molecules, and that cost in energy to do so is essentially the chemical potential of the system. So it is not a force that you can apply in the sense that you can apply pressure or an electric field or magnetic field, but it is a generalized force in this sense. That it is one of the F's that we can write down in the first law of thermodynamics. We are not going to look at this very much. We are going to restrict ourselves to cases where you have fixed amount of gas or fixed amount of fluid, in which case this term drops out because n is constant in those cases. But just for completeness, this is the more general way of writing this. Okay. So much for the first law. Now what is the second law of thermodynamics, and that is a very profound one, a very deep one. Now several ways of enunciating it, there are many ways, and the elementary textbook ways of doing so would tell you things like it is impossible to get to the absolute zero of temperature in a finite number of operations and so on and so forth. But actually one should write this a little more precisely, and let us do it in terms of the various thermodynamic variables we have talked about here. Before that, I need to mention what is meant by a quasi-static process. I have already talked about this. I said that when you make a change of state, when you take a thermodynamic system and you do something to it, or it changes state, if it does so in a sequence of states such that at any given time it is in thermal equilibrium, then this process is a quasi-static process. In general, what it implies is that, very roughly speaking, you do not do too many sudden things to it, you do not make many rapid changes, although that is not necessarily something which guarantees a quasi-static process. But we have already seen what is meant by thermal equilibrium. A thermal equilibrium state is one in which all time averages are time independent. All averages of macroscopic quantities are time independent. Now when you make a change of state, if you ensure that you go through a sequence of equilibrium states, then we have a quasi-static process. Okay. In a quasi-static process, certain remarkable things happen. One can show that in all such processes, dq, this quantity, is less than equal to, if you divide by the absolute temperature, this is less than or equal to the perfect differential of a state function. This is less than equal to the differential of the entropy. This, if you like, is the content of the second law of thermodynamics. So for all quasi-static processes, well, I should say this a little more carefully. For all processes, dq over t is less than equal to ds, and for quasi-static processes, dq is over t is equal to ds. Okay. So that is the right way to say it. And if you like, this is the second law of thermodynamics. The formulation in this form, it is most convenient for us to proceed further. So the inequality which says the change in the entropy is always greater than or equal to dq over T becomes an equality in the case of quasi-static processes. So it says or dq equal to TdS. So the significance, one significance of a quasi-static process is that 1 over T acts like an integrating factor. So notice that this thing here is 1 over T, an integrating factor, times an imperfect differential becomes a perfect differential. So this quantity is an integrating factor. Just as 1 over P was an integrating factor which multiplied dW to give you dV, in exactly the same way dq, this imperfect differential multiplied by this integrating factor gives you the derivative, gives you the differential of the entropy. So if you put that in, this is the second law, if you put that in, this implies that du is TdS minus PdV plus mu dN. Because I write this as TdS, and then you see immediately that this implies that u as promised is a function of these state variables. The internal energy of the system is a state function and it is a function of the extensive variables, the entropy, the volume and the number here. This is the content of thermodynamics essentially. There is another law, there is by the way a zeroth law and there is a third law, and I will mention that very briefly, very shortly, but this specifying this specifies, as far as a single component is concerned, system is concerned, the thermodynamics completely, that is it. Once you tell me what this function is, I tell you everything about the system that is thermodynamically knowable about the system. So this is the content of putting in the first two laws. Now just one quick remark about the zeroth law. The zeroth law helps you to define the temperature in terms of these quantities, because it says if u is a function of S, V and N and you keep V and N constant, it is clear that du is then TdS. So therefore this will imply immediately, this implies that T is the rate of change of the internal energy with respect to the entropy, given that the other two are kept constant. So this is the notation which says these two independent variables are kept constant, and then this coefficient must necessarily be the rate of change of u with respect to S. All you got to do is to put these two equal to 0 and divide by du and take divide by ds and take the limit here. Similarly, in exactly the same way, you immediately find also that the pressure is equal to minus delta U over delta V, keeping S and N constant, and the so called chemical potential is the derivative of du with respect to N, keeping S and V constant. This is at this stage purely mathematical, because you may ask in physical practice, how do I keep the entropy constant, how do I can keep the volume constant, we can physically see this, how do I keep the entropy constant? That is a non-trivial question to express, but in mathematical terms it is clear that these partial derivatives actually give you these coefficients here. So this is the content of the first two laws of thermodynamics. If you like, the third law of thermodynamics actually says, the first law says, the zeroth law says that there exists a quantity called the temperature, etc. I mentioned that in thermodynamics you use the ideal gas equation of state to define the Kelvin scale of temperature. If you like, this defines the temperature here. This quantity here defines the rate of change of the internal energy with respect to the entropy at constant V and N, helps you to define the temperature. Not a very useful definition as it stands here, but when you go to statistical mechanics it becomes an obvious kind of definition. Okay. Similarly for the pressure and the chemical potential there. The third law of thermodynamics is something different. It says that if this derivative is 0, there exists a state in which the entropy also vanishes. Okay. That is equivalent to saying that the entropy of a system vanishes at absolute 0 of temperature. So we will come back to that and talk about it a little later. Yeah. Okay. So we are not going to use the third law of thermodynamics as such, but I thought I should mention it in the interest of completeness. We will get back to this.